In one of the previous lectures, we learned that the streamlines within and outside of a boundary layer must bend slightly outwards away from the wall to satisfy conservation of mass as the boundary layer's thickness grows downstream. That means even if we have a horizontal wall, the streamlines will not be horizontal. Instead, they will form a horizontal line. For a given downstream distance, the amount of displacement is called the displacement thickness. In this video, we will discuss the displacement thickness of a boundary layer. The displacement thickness, given the symbol delta star, is defined as the distance that a streamline just outside of the boundary layer is deflected away from the wall due to the effect of the boundary layer. To derive the equation of the displacement thickness, we perform a control volume analysis using the mass conservation principle. First, let's describe the control volume for the analysis. Its lower boundary is coinciding with the wall surface, whereas its upper boundary is coinciding with a streamline outside of the boundary layer. There's no flow passes through these two boundaries because, by definition, no flow can cross the streamline. Therefore, the flow enters the control volume through the left boundary, which is located at the leading edge of the flat plate, and leaves the control volume through the right boundary, which is located at a downstream location along the plate. Notice that the height of the left boundary is h. While the height of the right boundary is h plus delta star. At the entrance, the velocity is not yet affected by the boundary layer, so the velocity is capital U. In the general form, the equation of mass flow rate is m dot equals to the fluid density times the average velocity times the cross-sectional area. Therefore, at the entrance, we have m dot 1 equals to the fluid density rho times capital U and times the cross-sectional area, which is h. But we put it in the integration form by integrating dy from 0 at the wall up to the height h. Notice that rho and capital U are constants, therefore we can put them in the integration or out of the integration. At the exit, we have m dot 2 equals to the fluid density rho times the velocity and cross-sectional area, which is given by the integration of U, the velocity within the boundary layer, dy from 0 at the wall up to the height h, plus the mass flow rate through the delta star, given by rho times capital U times delta star. By mass conservation, the mass flow rate enters the control volume is equal to the mass flow rate exits the control volume. So, we equating m dot 1 and m dot 2. we can cancel out the density rho. Then we rearrange for delta star. The two integrations on the right hand side can be combined like this. Finally, we have delta star equals to integrating from 0 to h 1 minus u per capital U dy. Since h is arbitrary, we can replace it with the infinity sign to indicate that the integration is valid for as long as the distance is far enough from the wall, such that it is beyond the boundary layer thickness. Based on this equation, we can determine the displacement thickness, delta star, if we have the quantity u per capital U, which is the velocity profile of the boundary layer flow. Do we have that quantity? The answer is yes for laminar boundary layer. Remember that Blasius has obtained a solution for the laminar boundary layer. When we apply that velocity profile to this equation, we obtain this relation, where the displacement thickness delta star is equal to 1.72 x per the square root of Reynolds number x. Comparing the displacement thickness with the boundary layer thickness, we can see that the displacement thickness is about 35% of the boundary layer thickness. Let's look at the physical significance of displacement thickness. One obvious example is flow bounded by walls. Suppose you are testing the aerodynamic properties of a car model in a wind tunnel, and the test section has parallel walls. Since the cross-section of the test section is uniform throughout the length of the test section, you might expect the flow to be uniform as well, but that would not be the case due to the effect of boundary layer. Instead, since the flow velocity within the boundary layer is reduced, the ones outside of the boundary layer at the central region must increase, such that the overall flow rate is maintained the same. Now, for a downstream distance, how much the flow velocity will increase? To answer this question, we can determine the displacement thickness and find out how much the effective cross-sectional area of the flow has reduced. Then, we use the continuity equations to calculate the velocity based on the reduced cross-sectional area. This is the end of the video. Thanks for watching.